Hello and welcome everyone to our 8R notes lecture. So in our lecture today, we are going to cover some physics theories and some physics formulas. Now 8R Notes is a company that provides free and paid resources for students. Some of our free resources are study notes, lectures like this one, discussions, videos on YouTube, newsletters, an 8R calculator, which I know you guys will be using throughout the year. We provide you with articles and a lot more. Some of our other resources which you need to pay for are TuteSmart, which is private tutoring. I would highly recommend you have a look at TuteSmart because a lot of the tutors there have gotten really good scores, so they can help you a lot. Study guides, they are the printed version. There are some printed revision materials with top tips to help you get great marks. And obviously there is Ed Unlimited, which has a lot of study guides and practice stacks and practice exams in one place. Now we would like to give a special thanks to La Trobe University and our other partners such as RMIT, Deakin, UTS, and Macquarie for making this lecture possible. So what are we going to cover today? In our 3-4 lecture today, we are going to cover some concepts about motion and fields, some about DC motors, Faraday's laws, alternators and transformers, and ultimately a bit of special relativity. Here are a couple of things to know from units 1 and 2. You need to know the 3 laws of motion, the constant acceleration formula, of course, how to do vector addition, momentum and impulse, and the concept of work, gravitational spring, and kinetic energy. So a lot of these concepts, right, that you have learned in year 11 are now assumed knowledge, but don't stress because a lot of teachers do explain them again in year 12, because obviously you can't remember everything that you studied the year before, so it's a good idea to repeat some of the concepts. Now, Newton's 3 laws of motion is referring to the first, second, and third law. First law that says that as long as there is a force being applied on an object, then the acceleration will be different from 0. So if the net force on an object is different from 0, acceleration will also be different from 0. And if an object is traveling at a constant speed or is at rest, then acceleration will equal to 0. There's the constant acceleration formula. So all the v squared is equal to u squared plus 2ax, v is equal to u plus at, x is equal to ut plus half at squared. These are the main ones that you need to remember. Obviously you have other ones, but these are the main ones. You need to remember how to do vector addition, and if you recall vector addition, we learned it by saying the head to tail method. So if you have one vector going to the right, one vector going up, a vector addition will essentially be from one point to another point, right from head to tail. And of course vectors are represented with arrows. How about momentum and impulse? For momentum and impulse, you need to remember that momentum is essentially mass multiplied by velocity, and impulse is force multiplied by time. So these are the 2 formulas, and you need to remember the law of conservation of momentum as well. You need to recall the concept of work, which is force multiplied by distance, but sometimes you also need to include the cos theta if the force is being applied at an angle and not in the same direction as the displacement of the object that the force is being applied to. How about gravitational spring and kinetic energy? You just need to remember the general formulas, the gravitational energy formula, which was gravitational potential energy, which is equal to mgh, spring potential energy, which is equal to half k delta x squared, and kinetic energy, which is equal to half mv squared. Some important things to note that we might learn that we are going to cover together is how to actually answer questions for examiners. The best way to do that is to write the formula out, then substitute everything. The reason for that is because you get a substitution mark and you get 1 mark for the final answer. If you don't write out the formula, then you might only get a mark for the answer and no mark for the substitution. Or if you get something wrong, you will only get a mark for again the answer and no marks for the substitution. But if you get the answer wrong, obviously you won't get the final mark because you have the correct final value. You don't have the correct final value, but you have the correct substitution. Maybe it was because you were rushing with your calculator. Maybe because of that, you got the wrong answer. But given that you substituted correctly, you still get 1 mark out of 2. So writing out the formula and then making the substitution is really important. Now, worded answers are something else that you need to be wary of. Always put them in dot points and you need to be concise. I would say explain the theory and put it back in the context are the 2 main ones. You can make a final statement if necessary, but talking about the theory in general and then applying it to the context of the question is it's really, really important. For example, if the question asks, explain why an EMF, an electromagnetic force, is generated in the wire loop as the magnet approaches the loop, so we're talking about this case, it's talking about Lenz's law, you need to state that Faraday's law, so the theory, you need to state the theory. Faraday's law states that if there is a change in magnetic flux, EMF will be generated according to the formula and multiplied by change in flux over changing time. As flux is equal to magnetic field strength multiplied by area, if magnetic field strength changes, the flux will also change. Hence, as the magnet gets closer to the loop, the magnetic field strength increases, changing the flux and generating EMF. Right? So you relate it back to the context of what you see. That's what it means to relate it back to the context of the question. Now let's talk about Newton's 3 laws. Before I just skimmed through it, but now let's cover it in a bit more detail. You do need to know these laws by heart though. And if you don't, I would highly recommend you have them on your cheat sheet. So let's start with the first one. Let's start with Newton's first law. According to Newton's first law, an object will remain at rest or travel with a constant velocity if the net force acting on the object is 0. The acceleration of an object is directly proportional to the force applied and inversely proportional to the mass of the object. And then the third law, which is what most students get incorrect. The third law states that if an object A exerts a force on object B will exert an equal and opposite force on object A. So force of A on B is equal to negative the force of B on A. Note that these forces act on different objects. Now, what does that mean, and why do so many students get this question incorrectly? I actually remember very well there was a question on the VCE exam in regards to this that only about 1% of students got correctly. The reason for that is because students really get confused with action-reaction force pairs. If you are standing on the ground, and there is a weight force acting on you, if I were to ask you and stop and think for a minute, what is the reaction force of the weight force? A lot of you would say, oh, it's the normal force. And that is the wrong answer. The reaction force of the weight force on you is also a weight force. It's the weight force that you apply on the earth upwards. Hence why it says that these forces have to act on different bodies. They can't be acting on the same body. So the reaction force of the weight force that the earth applies on you, right, on people, is the reaction force of that is the weight force that the person applies on the earth. So there are three characteristics for action-reaction forces, or there are three characteristics that action-reaction forces need to satisfy. One of them, they need to be equal in size. The other one is opposite direction. The third one, they must be of the same type. Same type of force or act on different objects. So it's a weight force with a weight force, right? Those are action-reaction force pairs. So some of you might be thinking, well, if that's the case, then obviously the question arises, what about the normal force? Well, the reaction force of the normal force that the ground applies on the person is the normal force that the person applies on the ground. So those are the action-reaction force pairs that we usually talk about. What you've learned before, that the normal force is the reaction force of the weight force, that is not true, at least not according to the third law of motion. Now, let's talk about the constant acceleration formulas. Now, if you know them by heart, obviously there's no need to include them on the cheat sheet because you know them by heart. If you don't know them by heart, still, whether you should include them on your cheat sheet is up to debate because Vika will provide you with a formula sheet that will have these formulas there, so I don't know how useful it will be to have to repeat the same thing that you already have in front of you and take up the space available on your cheat sheet. Now remember that the variables are displacement, which is measured in meters. I prefer using x, not s. U is the initial velocity in meters per second. V is the final velocity in meters per second. A is the acceleration and T is the time. And time is measured in seconds, of course. Now let's talk a bit about projectile motion. When we are talking about projectile motion, you need to remember that we're looking at motion in 2 dimensions. So usually, what does that mean? Well, usually when we are talking about a motion question, usually what Vika would do is they would give you an example where they're saying, oh, there is like this on the ground, there is a car pulling, I don't know, something, right? Like a boat. So motion in that example is only one dimensional because you're only looking at one dimension of motion, left and right, or only horizontal motion. With projectile motion, something is being shot at an angle, and it's following a path which includes both vertical displacement and horizontal displacement. So you can break up the velocity into 2 components because remember, velocity is a vector. It has a horizontal component and a vertical component. You can use the head to tail method, right, to break down the velocity into its constituent components and you'd get a particular value. But how do we do that? Well, to find the horizontal component of velocity, we say that Vx is equal to V cos theta. And to find the vertical component of velocity, we usually use the formula V y is equal to V sine theta. Now, if we were to draw, this is how projectile motion would look like. There is horizontal displacement and obviously vertical displacement. Now, the horizontal velocity, which is a really important point to mention, remains constant because there is no force acting on the ball. Think about the projectile when it's up in the air, right? When you throw a projectile and it is up in the air, what is the force acting on this projectile after it has been shot and it's mid-air traveling? Well, obviously, if let's say you're shooting a baseball with a bat, initially it's the first contact that the bat has with the baseball that provides the force for the baseball to fly at the projectile. However, for the baseball to fly at an angle means that there is a force acting on it, and that is the weight force, because mid-air there is still weight force acting on the baseball. So the weight force pulls down the baseball, and that's why the baseball falls to the ground. That's why it slows down and falls to the ground. However, in the horizontal dimension of its motion, there is actually no force acting on the baseball, because the weight force acts downwards, right? At any point in time, the weight force has a constant value because it's mg. The mass of the baseball is the same. G is the same as well. It's a constant, 9.8. So the force acting on the baseball is the same on the vertical plane, but it's nothing on the horizontal plane. So what are some key points about projectile motion? The only force acting on the projectile is gravity. The horizontal and vertical velocities are independent of each other. The horizontal velocity is constant. The vertical velocity changes due to gravity, but the acceleration is constant, and hence any of the constant acceleration formulas are applicable. I have to mention that there are 3 types of projectile motion which are very common on the VCA exam. The 3 common types of projectile motion questions would be a symmetrical projectile, a projectile which is so short and then it falls down asymmetrically, and a projectile that just falls off the edge of something. Now, if you cover how to do those 3 types of projectile motion questions, then you should have your bases covered for... You should have everything, your bases covered for the final end of the year exam. Now, remember that forces are vectors, and vectors can be added. When dealing with forces, obviously we use a lot of vector addition and Newton's second law. But 2 very important cases that you guys need to remember and that we will review now when it comes to motion questions are inclined planes and tension. When it comes to inclined planes, 2 forces act on an object on an inclined plane, excluding friction. There is the weight force and the normal force. When it comes to friction, one thing which I forgot to mention is that for projectile motion, we will assume air resistance is equal to 0. So you have to ignore the effect of air resistance in your calculations because it gets complicated. But you do need to qualitatively interpret what air resistance does, what impact it has on the projectile. On the projectile, air resistance affects the projectile path. It will shorten the projectile path in both the vertical and horizontal plane. So if there is air resistance present, the projectile will reach a lower height and a smaller range. Range is the horizontal displacement of the projectile. Then if there were no air resistance, the projectile could reach a higher height and a longer range. Again, you only need to interpret the impact of air resistance qualitatively, not quantitatively. So there is no need to stress out about this one. Now back to inclined planes. Vika will always ask you guys how to draw forces on an inclined plane. When Vika asks that question, what they are specifically looking for is you drawing the normal force perpendicular to the plane on which the object is standing, to that surface. For the weight force, they are looking that you guys draw it from the center of an object's mass straight down. They want you to annotate very well the forces, right? They want you to label what you're drawing. It is really important. If you don't label what you are drawing, it is very, very likely that you will get 0 marks. Then they ask you sometimes to draw the net force with a dashed line. For an inclined plane, drawing the net force with a dashed line will essentially be a dashed line going downwards following the slope of the inclined plane. But if the question is about a banked track, then the net force would have to be going towards the center of the object's motion, because a banked track is like a velodrome. And the whole point of a banked track is that the normal force provides enough, the normal force in combination with a weight force will result in a centripetal force. But centripetal force is a force that acts on an object towards the center of the object's motion. So be very careful when Vika asks you to draw forces. Be very careful if it is an inclined plane it is talking about or a banked track. Now, tension is absolutely the most difficult topic on the exam. Year after year after year, Students make a mistake when they answer tension questions. Because tension is its own reaction force. That's the problem with tension. It is its own action-reaction force. Tension is the force in a rope or an object that is created when something pulls on it. Many people struggle with this question, as I said, because they are interested in the magnitude of tension, and there is a lot of difficulty with students to find the magnitude of tension. And the best way is to illustrate the example that they're giving to you. The best way is to draw out what they're trying to explain to you. So always use a force diagram. Always draw a force diagram when you're dealing with tension questions. For example, for a pulley system or for a spring system, those are the ones that usually ask tension questions. So if we're talking, for example, about a pulley system, first of all, you need to try and find the acceleration of the entire system by looking at the system as a whole. So in the case of a pulley system, right, in the case of a pulley system, and I will draw it here so it's easy for you guys to see. So as I said, in the case of a pulley system, first of all, you consider them as a connected body and try and find the acceleration of the system as a whole. The only force acting on them initially is the weight force, which pulls on the mass here. Let's call it mass 1 and the mass at the top, mass 2. So acceleration will be equal to the net force divided by masses of both bodies. So that would be F net divided by M1 plus M2. And therefore, it will give you a magnitude of the acceleration. After you find the magnitude of the acceleration, you have to find the tension which acts on M2. To find the tension, you use the formula M2 multiplied by the acceleration that you found initially. This is basically referred to as using Newton's second law. So, finding the acceleration of the entire system and looking at the system as a whole, once you have the acceleration, use Newton's second law to find the tension by looking at the individual component. Like in this case, I looked at M2 individually. You will most of the time be successful in finding the value of tension. It works most of the time if you are stuck, so I would highly recommend that you give it a go. And also be very careful with signs and directions. Now let's go on to the topic of energy. Energy is the ability of an object to move. There are three types of energy: gravitational potential energy, kinetic energy, and spring energy. Gravitational potential energy is equal to mgh. Kinetic energy is equal to half mv squared, and elastic potential energy is equal to half k delta x squared, where m is the mass in kilograms, g is the gravitational field strength in newtons per kilograms, h stands for height in meters, and v stands for the velocity in meters per second, whereas k is the spring constant and x is the extension and compression. According to the law of conservation of energy, for an isolated system, the total amount of energy is conserved, but it can be transferred or transformed. So the final point here relates to the fact that energy cannot be created or destroyed, it can only be transformed from one form into another. And hence the Batman meme. How about work? Well, work is defined as the change in energy of an object. And it can also be found as force multiplied by distance if the displacement is linear. But given that definition with that formula, it means that work is also the area under a force distance graph. When the force acting on the object is not constant. Because if the force is not constant, at any point in time, the value of the force is different. But how do we find force using the area of the graph? Well, let's consider work done for 3 meters of displacement. The work will be the area under the graph. It will be this area here. And how do we find that area there? Well, we count the number of squares in the shaded region, and we multiply it by the area of one square. The area of one square can be found by multiplying 0.5 with 0.5. Now, obviously, this works only and only if the displacement shown is in meters. Now, let's talk about springs. Springs are the second topic, which are one of the worst done topics on the exam after tension. It comes up pretty much every year on the exam, and today we will focus on oscillating spring, where the spring is hung from the ceiling and there is a mass attached to it. There are two perspectives that you can take when looking at springs. The first one is looking at Hooke's law, where force is equal to negative k multiplied by delta x. Note that k is the gradient of a force distance graph of a spring. It's the gradient here, it's the rise over run. The energy will be the area under that graph. This is the oscillating spring I was referring to before. Let's discuss what happens in a spring at 3 different points of its oscillation in terms of energy and forces. At the top, the spring has maximum, here it has maximum gravitational potential energy, but because it's not moving, it has 0 kinetic energy and 0 elastic potential energy. Midway through, it has maximum kinetic energy, but its gravitational potential energy is half of what it was before because it's half the height now above the ground. And the elastic potential energy has increased in value. How about at the bottom of the motion of the spring? At the bottom of the motion, the spring has maximum elastic potential energy, no gravitational potential energy, and no kinetic energy. So in this setup, you can observe the law of conservation of energy, because all the energy that was stored in the spring at the top in the form of gravitational potential energy has now been transformed into elastic potential energy. And midway through, obviously, transformed into kinetic energy as well. Now, you do need to know the formulas that gravitational potential energy is mgh, kinetic energy is half mv squared, and elastic potential energy is half k delta x squared, where k is the spring constant and x is the spring extension or compression. Now keep in mind, the k constant is, another way to think about it is the stiffness of the spring, because the higher the value of k, the stiffer the spring is, basically, the more difficult it is to compress it. Let's look at oscillating springs at the top, middle, and bottom of the motion. Let's look at the graph. According to the graph, at the top of the motion, there is maximum gravitational potential energy. And then the gravitational potential energy linearly declines down to 0. Because obviously, the formula is linear. Then in blue, we notice the spring potential energy, which increases exponentially. The reason for that is because the spring potential energy is exponential. And in purple, it's the kinetic energy, but it looks like an inverted parabola. The reason is it's because it is, right? It's still an exponential graph. What is interesting about this slide, though, is that the weight force, of course, it's constant. The force that is applied by the spring obviously linearly increases the further the spring falls down, right? And the net force will essentially be somewhere in the middle. What is interesting is that the net force will equal to 0 when kinetic energy is a maximum. Therefore, In fact, kinetic energy is the maximum because the net force is equal to 0, because then that's when acceleration equals to 0 before it changes sign, right? So before acceleration changes sign here, acceleration first of all equals to 0, and that enables kinetic energy to be a maximum because that's when velocity is at its peak. Now, let's talk about momentum for just a little bit. Momentum is the mass in kilograms multiplied by velocity in meters per second. Momentum is loosely thought of how hard it is to make an object stop. We never write this down, but it's nice. It's a nice way to think about it. It's a more structured way to think about it. It's more intuitive, basically. The law of conservation of energy states that momentum in a collision is always conserved. How about impulse? What do we need to know about impulse? Now, actually, let's go back to momentum a bit. According to the law of conservation of momentum, means that momentum before collision equals the total momentum after collision. I would highly recommend you guys draw graphs. So what happens before collision? One object goes towards the other. And then the objects collide. In this case, there are three scenarios that can happen. Usually with momentum questions, there are again three scenarios, just like with projectile motion questions. The two objects collide and then they move together in the same direction separately. They collide and they move in opposite directions separately. Or they collide and they move in the same direction but combined, attached to one another. But the general idea stays the same, that m1u1 plus m1u1 plus m2u2 is equal to m1 v1 plus m2 v2. So, according to the law of conservation of momentum in a collision is always conserved. That means that the momentum that one object gains, the momentum that one object loses, the other object will gain. But momentum being conserved is not the same as velocity being conserved, right? Whatever speed an object loses, not necessarily the other object will gain. Now let's talk about impulse. Impulse is a measure of the change in momentum of an object when a force acts on it. Impulse is equal to mass multiplied by velocity and force multiplied by time. Impulse is acting on an object, is measured in kilograms meters per second or newtons seconds. M is the mass of the object in kilograms. Delta V is the change in velocity in meters per second. F is the force in newtons, and delta T is how long the collision lasts for in seconds. Due to the law of conservation of momentum, the magnitude of the impulse acting on an object is equal to the magnitude of the impulse acting on the other object in a collision. They just act in opposite directions. So something cool to note about this. If you catch an egg, you've applied an impulse on the egg by making it stop. For a given mass and change in velocity, the impulse is constant. If you increase the time of the collision, the force acting on the egg decreases by making it less likely to break. And I remember back in year 11, this can be done by moving your hand as you catch it, which is cool. Back in year 11, our teacher did a really cool experiment. He set up a massive blanket, right, that two people were holding. And then he gave all the rest of us an egg. Not a boiled egg, just an egg. And he said, throw it at the blanket. And we started throwing it with as much force as possible, with all our might. And no matter who it was, how hard they tried to throw the egg never broke. And that was really cool, because it showed how the importance of impulse. It showed that force is equal to impulse divided by time. So for any form of collision, if the impulse is constant, you can increase the time of collision. And that is the whole idea with crumple zones in cars, right? Crumple zones in cars are designed to crumple, to be reduced down to nothing, because that increases the time of the collision, significantly reducing the force applied on the driver, therefore drastically increasing their chances of survival. However, since we are on the topic of momentum, we also need to talk about elastic and inelastic collisions. In a collision, momentum is always conserved. Kinetic energy is not always conserved, though. It can be converted into heat, sound, or deformation of the objects. There are two types of collision. One is an elastic collision, where the kinetic energy is conserved, and the other one is an inelastic collision, where the kinetic energy is not conserved. To determine whether a collision is elastic or inelastic, you must calculate the kinetic energy of all objects before and after the collision. Well, some of you might ask, what does that mean and how do we do that? Well, essentially, kinetic energy before the collision should be half m1 v1 square of that object plus half m2 the velocity of that object. This is before the collision. After the collision, kinetic energy of the system should be half, again, m1 v square plus half m2 v square. So this is u, and then vv. If kinetic energy, and you have to state this on your exam, if kinetic energy before the collision is different from the kinetic energy after the collision, then the collision is inelastic. If the kinetic energy before the collision is the same to the kinetic energy after the collision, then the collision is elastic. Usually, elastic collisions only occur with subatomic particles. Now, another topic of motion that we can talk about is circular motion. Circular motion is literally looking at things that travel in a circle. There are three types of circular motion: horizontal circular motion, vertical circular motion, and backed tracks. The properties of circular motion are centripetal acceleration and the centripetal force. The centripetal acceleration is the acceleration towards the center of the circle, and centripetal force is the net force acting on an object that is towards the center. The velocity in this case is tangential to the path. The formula for centripetal acceleration is v squared on r, but because v is essentially distance over time, and if you square it, you divide by r, you'll get the formula here. Because distance is 2 pi r, right? So it's 2 pi r on time. You square that, you get 4 pi square r divided by t square. And then you have the radius, so you cancel the radius. So you're left with 1r, 4 pi square r on t square. And obviously, to find force, you just multiply the acceleration by mass of the object. Now, what's even more important here is the fact that you have to multiply by is how to actually draw. This is the most important part. You have to actually learn how to draw what I just described onto there, basically. The way to draw that is by making sure acceleration and the net force is literally towards the center, and velocity is just going on a tangent. It's really important to draw the velocity component as in a tangent. Now, obviously, we said that circular motion can appear in three different ways. One way that it can appear in is essentially the one you see here. We call this circular motion that occurs on a horizontal plane, where the speed of the object is constant. The velocity of the object is changing, however. And this is the least complicated type of circular motion. There is also the type of circular motion that occurs on a vertical plane. Speed is not uniform. You can think about energy transformations. And you only need to consider the top and the bottom of the circle. Vika will not ask questions about what happens on the sides of the circle. At the bottom of the circle, the net force is upwards because the normal force is greater than the weight force. Whereas at the top of the circle, there's supposed to be a car here, sorry for that. The net force is downwards because the normal force is smaller than the weight force. Now notice that we're saying the normal force is greater than the weight force or the normal force is less than the weight force. We are not talking about the weight force itself because guess what? The weight force, when it comes to the weight force, it's actually constant, whether it is at the bottom of the circle or at the top of the circle. And obviously be careful with signs. Now, I do need to cover one small thing before we continue. And that is apparent weight, apparent weightlessness, and true weightlessness. Now, obviously, not obviously, but this is not technically speaking directly on study design, but Vika still assumes you know it. So that's why I'm explaining it. The normal force is obviously our perception of the weight force because we can't feel our weight force, but we can feel the ground pushing us up. Therefore, apparent weight describes how heavy someone feels, and this is related to the normal force. If the normal force is greater than the weight force, then the person will feel heavier than they usually feel, because usually they're standing on the ground still, and the normal force is equal to the weight force. So their usual perception of our weight, so our perception of our own weight, is actually right because the normal force is actually equal in magnitude to the weight force. It's just acting against us, right? So that's how we can feel it. But when the normal force is greater than the weight force, all of a sudden we think that we are heavier. And when the normal force is smaller than the weight force, all of a sudden we feel lighter. That means that at the bottom of a circle, let's say at the bottom of a circle, a car driving, I don't know, like down a hill in a valley, all of a sudden you will feel lighter, and all of a sudden, you will feel heavier, because the normal force is greater at the bottom of the circle than the weight force, so you feel heavier than usual. Then at the top of a circle, the normal force is smaller than the weight force, therefore you feel lighter than usual, because usually the normal force is equal to the weight force. So that's what apparent weight is. Therefore, apparent weightlessness occurs when the normal force for a split second is equal to 0. But the gravitational force is not actually 0. That is true weightlessness. True weightlessness occurs when the real weight force is equal to 0. Now let's think about circular motion and banked tracks a bit more. Circular motion that occurs on an inclined plane, like a velodrome, is circular motion that is occurring on a banked track. Now, the object is traveling at the design speed, which is the speed an object travels at, so that the friction is not needed to keep the object in track. That is, tan theta is equal to v squared divided by rg. The net force is towards the center and not down the plane. The triangle of forces can be connected with the circular motion formula, mv squared on r. The most important thing here is to remember to draw the net force acting towards the center. Also, remember the design speed, which is, to find the design speed, you have to use this equation, or the design angle, tan theta is equal to v squared on rg, right? Right here. You can rearrange to find the design speed, or you can say theta is equal to inverse tan of v squared on rg, and then you will find the design speed. Now let's start looking at fields for a bit. What is a field? Well, a field is something that alters a region of space. When two fields interact, they apply a force on each other. How can we represent fields? We represent fields using vectors, which only applies to one point in a region of space. The direction of the arrow indicates the direction of the field. The length of the line determines the length of the field. Field lines applies to a large region of space. Now, the properties of the field that we are talking about depends on the type of field that we are, again, considering to talk about. If we consider a gravitational field, it's a field that is created due to mass. When two gravitational fields interact, there is an attractive force between the two masses. The properties are that they are only attractive forces. They only apply an attractive force. It's a monopole. It only has one pole. And the shape is radial. The arrows point inwards and the field is stronger near the mass. The formula that we use is this inverse, the inverse square law formula, where the gravitational field strength is equal to gm on r squared, and the force is obviously the gravitational field strength multiplied by mass, right? The weight force is usually mg. So the only thing that has changed here is how we define g. Now keep in mind that g is the gravitational field strength. That's the lowercase g, capital G is gravitational constant, which is 6.67 times 10 to the power of negative 11. Then there is mass, which is the mass of the object being orbited in kilograms. Then there's the mass of the object doing the orbit, which is lowercase m. The radius of the orbit in meters must be measured from the center of the object, and Fg, which is the gravitational force in newtons. Now we must also keep in mind to not forget about satellite motion. So objects which orbit around a planet is what we call a satellite. Now, because satellites move around in circles, almost in circles. For VCE purposes, we will assume their motion is in perfect circle. It means that in that case, the gravitational force acting on them acts as a centripetal force, because it is the only force acting on the satellite. Therefore, the satellite is in freefall. A person in orbit has no normal force, therefore they will experience apparent weightlessness and not true weightlessness, because there's no normal force. When you're in a spaceship, you're floating around. Now, let's not forget something about satellites. There are some satellites that we call geostationary. Geostationary satellites are satellites that are stationary relative to a point on the Earth's surface, right? Now, satellites can be natural or artificial. They are natural like the moon or artificial like man-made. But they are geostationary when their period of rotation is equal to the period of rotation of the Earth around itself, and they are above the same point on Earth, therefore they are above the equator. But going back to the thing that we said that, okay, the satellite orbits in a circular motion, therefore it's going to experience centripetal, therefore the weight force acting on the satellite must be centripetal force. It means that we can equate those two. We can say that the weight, gm multiplied by lowercase m divided by r squared, is equal to mv squared on r. If we simplify that, we get Kepler's law, which is r cubed on t square. It's r cubed on t square. Which is equal to gm on 4 pi square. Now let's talk about the changes in satellite energy. Because there are two types of energy associated with an object in orbit. There is gravitational potential energy and there is kinetic energy. These amounts change when the radius of the orbit changes. Normally, we would use mgh to find the change in gravitational potential energy as the height changes, but because g is changing, we cannot use this formula. Therefore, we have to use the area under a graph, like we did before. So I'm not going to spend too much time on it, given that I assume you guys know how to do it, which is area under the graph is the number of squares multiplied by area of one square. The change in energy in this case, for example, a satellite which now moves to a lower orbit from a higher orbit to a lower orbit, that change in gravitational potential energy will obviously be converted into kinetic energy. But now let's talk about electrical fields. Now, electrical fields are fields which are created by an electric charge. A point charge is a charge created by a single point, example, a proton or an electron. The properties of the point charge are that it is radial, field is stronger, closer towards the point charge, it is made up of monopoles, and the arrows point away for a positive charge, or the arrows point inwards for a negative charge. The electric field strength is equal to kq divided by r squared, where E is the strength of the electric field, K is the Coulomb constant, Q is the charge of the point charge, and R is the distance from the charge. Oppositely charged particles create an attractive force for each other. Like charged particles create a repulsive force against each other. You do need to know to remember how to draw this. Now, the formula here is very similar to that of the gravitational potential energy. So instead of G, capital M, G, so instead of using this formula, we're using this formula. So it's actually very similar to one another, where in this case F stands for the force on the charge, K stands for the Coulomb constant, Q1 stands for charge of the first point charge, Q2 stands for the charge of the second point charge, and R is the distance between the centers of the two charges. Now, notice the diagrams. In the diagram, there is nothing in between the negative charges. The reason for that is because we said that field lines are vectors. Therefore, they would cancel each other out in the middle. Second of all, let's talk about KQ1, Q2 divided by R squared. In this case, we are referring to the fact that if we're looking at a proton and an electron revolves around a proton, right? So we can use this formula to find the electric force which is being applied on the electron by the proton, and obviously the force that the electron applies on the proton. Now, two oppositely charged plates create a electric field. And this is known as a dipole, indicated by the evenly spaced parallel lines. Putting a charged particle in the field will cause it to move towards the oppositely charged particle. Hence, work will be done on the particle. The field that you see here is different from a radial field, right? Therefore, we call this a uniform field, where the electric field strength is voltage divided by distance, force is equal to Q multiplied by E, and work is charge multiplied by voltage, where electric field strength is the strength of the external electric field, V is the voltage, D is the distance between the plates, F is the force in newtons, Q is the charge of the point charge, and W is the work in joules. So let's have a go at this question here. An electron is placed between two electric plates, which are placed 30 centimeters apart and have a potential difference of 20 volts. What is the force acting on the electron? Well, you know, voltage is 20 volts divided by a distance of 0.3. You can find the electric field strength. Let me write that again, that looks awful. the force acting here on the electron would be what we found here, 66.7 multiplied by 1.6 times 10 to the power of negative 19. And obviously we have to learn about magnetic fields as well. Well, magnetic fields are essentially a field created by magnetism. And magnets are always dipoles. The arrows point away from the North Pole and they point towards the South Pole. Let's have a go at this question. How would we do this question? One second, I need to drink water. In this case, we know that magnetic field lines go from north to south, right? Same here, right? But we're only going to focus on these two arrows. The head to tail method tells us that the arrow is going diagonally down. If we displace that at point P, it would be like that. I know, it's a bit of an annoying question, but it is what it is. That's how we have to deal with it. Now, there is a connection between electric and magnetic fields. A moving charge will create a magnetic field. It makes a circle around the charge. Current is the movement of charge, hence a current will create a magnetic field as well. So these are the three right-hand rules that we talk about. We say that we can find the direction of the magnetic field based on the right-hand grip rule. So basically what we're saying is if there is a current carrying a wire, there will be a magnetic field induced by the current carrying wire. And the magnetic field will be induced around it. In order to find the direction of the magnetic field, we're going to use our thumb, and it will point in the direction of conventional current. That is current that flows from a positive terminal to a negative terminal, right? Whereas real current is current that flows from a negative terminal to a positive terminal. But we work with conventional current, right? Conventional. In this case, our thumb points in the direction of the current and our fingers wrap around the wire. That's the first right-hand rule. But there are different, but sometimes we need to represent fill lines which are going into the page and out of the page. A circle in the wire represents a current that goes out of the page. A cross in the wire represents a current that goes into the page. This can be remembered by thinking of an arrow. Use the right-hand grip rule to determine whether the magnetic field around these wires is clockwise or anti-clockwise. And let's do that now. So, let me explain it a little bit more again. If you think of an arrow that archers used to shoot, right? It has feathers and it has this metal piece at the front. Metal triangular piece. If you're shooting at the bullseye, from your point of view, when you're shooting towards the bullseye, you are looking at the feathers, which look like an X. Therefore, everything that goes into the page, fill lines that go into the page, we will note them with an X. With fill lines that come out of the page, therefore, we will note them with a dot. Because that is like an arrow being shot towards us, right? That's the best way to think about it. In this case, is the current going clockwise or anti-clockwise? Well, in this case, it's going, as you can see, it's going anti-clockwise. If something is going out of the page, obviously, it's anti-clockwise. If it's going into the page, it's going clockwise. Give me a second, guys. Now we know that a current creates a magnetic field. If the current itself is placed in an external magnetic field, like between two magnets, its own magnetic field interacts with the external magnetic field. When the two fields interact, they apply a force on each other. Consequently, a current in a magnetic field will have a force applied on it. Note that there is no force acting on the current if it is parallel to the magnetic field lines. You don't need to know why, you just need to know that that's how it works. So if we place a current carrying wire in a magnetic field, we want to know now the direction of the force that is being applied on the current carrying wire within the magnetic field. Because you have two magnetic fields interacting with each other, the external magnetic field and the magnetic field that is generated by the wire around itself. Therefore, a force will be applied on the wire. To find the force, we need to point our thumb in the direction that the conventional current is going. In this case, conventional current is going into the page. Our thumbs need to point to the direction of the magnetic field lines from north to south. Therefore, the force in this case would be applied upwards, so into the page from north to south. Therefore, the palm of our hand is indicating upwards. Therefore, the force being applied here is upwards. So how do we find the strength of the force acting on a current perpendicular to the magnetic field lines? Well, we find it by using the formula F is equal to N-bil, where F is the force in newtons, N is the number of turns of wire, B is the magnetic field strength, I is the current, and L is the length of the wire in meters. So let's have a go at this practice question for a bit. And these are Vega practice questions, by the way, so they're good ones. So F is equal to N-bil. Should we assume it's only one wire because it says a 13-meter piece of wire? P is equal to 0.2, current is 2, and length is 30 centimeters or 0.3, and you multiply them together. So the force in newtons is 0.12 newtons. Now let's look at charged particles in a magnetic field. A moving charged particle will have a magnetic field. When you put a charged particle in an external magnetic field, its magnetic field will interact with the external magnetic field to create a force. We can use the right-hand slap rule to determine the direction in which the charged particle now will move. The velocity of the charged particles acts as the direction of the current. Note that the force acting on the particle is always perpendicular to the velocity. This creates circular motion. The force from two fields acts as the centripetal force. So QVB will be the force by the magnetic field, where Q is the charge in coulombs, V is the velocity, and B is the magnetic field strength. But we also know that this motion, we also know that this is mimicking centripetal motion. That is, QVB is equal to mv squared on r. So let's remove the v from 1 second. QB is equal to mv on r. So r is equal to mv on QB, where r is the radius in meters, m is the mass in kilograms, v is the velocity in meters per second, q is the charge in coulombs, and b is the magnetic field strength. Now, two wires that are parallel to each other. So for the formula here, you can use this formula to find the radius that the charged particle, or the radius of the path of the charged particle. Now, two wires that are parallel to each other will exert a force on each other due to the interaction of their magnetic fields. How do we know whether or not this force is attractive or repulsive? Well, we use the right-hand grip rule and the right-hand slap rule. Now, let's continue with the other topics. If the current is in the same direction, it's the continuation of this. Cool. So if the current is in the same direction, they attract each other. But if the current is in the opposite direction, they will repel each other. How about when looking at current in a loop? Well, we are also interested in the direction of the magnetic field. Using the right-hand grip rule to determine the direction of the magnetic field inside and outside of the loop. We use crosses to indicate the magnetic field going into the page and dots to indicate the magnetic field going out of the page. So if current is going upwards here, we have to use our thumb going up. Our fingers will be curling towards ours. That means that you use dots to indicate things are going out of the page and X's to indicate that things are going into the page, inside the loop, in this case. How about solenoids? Well, for solenoids, we change the right-hand rule. We use our thumb to indicate the direction of the north, and our fingers curl in the direction that the wire is curling. If our fingers curl towards the page, the thumb will be to the north, the thumb will be to the left, therefore north is to the left and south is to the right. If our fingers follow the wire and they curl towards us, in a different scenario, then the thumb would be towards the south and the south would be towards where the north is now. So it depends. I like to think of it as the difference from a pull-up grip and a chin-up grip. Now let's talk a bit about DC motors and alternators. A motor is a device that converts electrical energy into kinetic energy using current and external magnetic field. Essentially, a force will be applied on one side of the coil, causing a continuous rotation. As the coil continuously rotates, again, that electrical energy will be converted into mechanical energy. However, there is one flaw with that. The coil needs to be connected to for a motor, the coil needs to be connected to a split ring commutator for it to work properly. Because the current needs to be reversed every half cycle in a DC motor to keep it rotating. A split ring commutator completes this function because a split ring commutator is a cylinder with a split in the middle. The cylindrical bit is connected to the coil. The rectangular bit is called the brushes and are connected to the terminals of the power supply. So what happens is that initially the current flows from D to C, causing the coil to turn clockwise. When a vertical position is reached, the gaps in the split ring commutator align with the brushes. Therefore, no current flows through the coil, but the coil continues to turn from the previous movement. The side of the ring that was initially in contact with the positive terminal is now in contact with the negative terminal, and vice versa, changing the direction of the current. The current now flows from C to D. Therefore, that's how split ring commutators work. But let's talk about flux a little bit. Flux is defined as the number of magnetic field lines passing through an area. And flux is equal to the magnetic field strength multiplied by that area. We can change flux by rotating the coil, right? Because by rotating the coil, less and less magnetic field lines can go through that area. However, when there is a change in flux, we are inducing a voltage. And we use this equation, which we call Faraday's law. We use this equation, which we call Faraday's law, where the number of loops multiplied by the change in flux divided by the change in time will generate a voltage. Now, a change in flux induces EMF, which is voltage, but not current. Current is only induced when EMF is induced in a closed circuit. So this is a quick practice question, which states a coil is turned from the vertical position shown to a horizontal position in 0.4 seconds. The coil has an area of 0.8 meters square and the strength of the magnetic field is 1.2 Tesla. What is the average EMF generated in the coil? Initially, you have to calculate the flux as B multiplied by A, and area is already given to you. Then, you put 0.8 at the top divided by 0.4 and multiply it by, so 0.8 multiplied by 1.2 at the top, divided by 0.4, 1.2 multiplied by 0.8, divided by 0.4, and you get 2.4. And it's only one coil, right? So 1 multiplied by 0.8 multiplied by 1.2 divided by 0.4. The answer is 2.4 volts. Now, it depends whether you use slip rings or split rings. If you use slip rings, the output will be AC, and the graph will look something like this. If you use a split ring commutator, the output will be DC, and the graph will look like the second one. Now, there's also the concept of the Lenz's law. The definition of the law is that any induced current in a loop will be in the direction so that the flux it creates will oppose the change in flux that produced it. Breaking this down means that Lenz's law is used to determine the direction of the current created when there is a change in flux, which induces a change in EMF, which induces current. The aim of the current is to create flux that opposes the flux that induced it. And these are the detailed steps showing that. Now, Lenz's law is not that complicated, so some tips for your year 12 would be to use the study design and do as many practice questions as possible. I would highly recommend you guys write up a summary cheat sheet before every SAC that you do. And if you do that, you will succeed, because that will help with memorizing all the formulas if you do a cheat sheet before every sack. And obviously you have to do a ton of practice questions throughout the year. If you do that, you should be fine, honestly. You can look at the slides. There are a lot of tips here that you can have a look at. If you have any specific questions, please do use the chat box, because it might prove helpful to you. Yes, and for a scientific calculator, I would say buy two. Always have one ready, one spare to go for the exam, especially. I would highly recommend you be cautious of that, because I've heard stories of people, oh my god, it's crazy. I've heard stories of people, their calculator breaking down on the exam, and imagine that, how stressful can it get? Oh my god, on the exam.